Okay, so in this video we're going to be talking about nuclear decay. In the last video we talked about the strong nuclear force, so I'm just going to recap that quickly. We talked about how the strong nuclear force was an attractive force between a certain very small range. We talked about how it affects all nucleons, and we talked about how it was extremely strong. So there are those three properties there, and the range that it's acting between at its strongest is 0.5 femtometers and 3 femtometers, and that will be important in a minute. Now we're going to take a look at this graph here. So this graph has neutrons on the y-axis, protons on the x-axis, and anything within the graph represents a single nucleus or single nuclei. This grey line here shows where n equals p. So any nucleus on this point here will have the same number of protons as it does neutrons. So that's basically how the graph works. Then this blue line here represents nuclei that are stable and won't decay. So you'll see that it actually follows the n equals p line for smaller nuclei, because they can have the same number of neutrons and protons and still be stable. However, as you start to get larger and larger in the size of the nuclei, they actually need more neutrons compared to the protons to remain stable. And this is because the more protons you add to a nucleus, you're increasing the effect of the strong nuclear force, but you're also increasing the repulsion of the electromagnetic force. And if you want to know more about that, you can look at my previous video. But as you increase the number of neutrons in a nucleus, you're not affecting the repulsion at all, but you're just increasing the effect of the strong nuclear force. So it's holding the nucleus together more and making it more stable. However, when we get to extremely large nuclei, and I'm talking within the hundreds of nucleons, we start to see that the size of the nuclei falls out of this 3 femtometer upper range, and when that happens, the strong nuclear force isn't as effective, and that can lead to unstable nuclei. And I will just show you that in writing here. So that's what I've just talked about here. And when a nucleus is unstable, it will do something called decay. And when it is unstable, we say that it is radioactive. So it will decay radioactively. So it will emit radioactive substances. And we'll look at that in a little bit more detail right now. So before I go into too much detail on decay, I want to just explain a little bit about how it was discovered. Now, I've already talked about how when a nucleus is unstable, it will decay, and what I mean by decay is it will lose mass, or it will lose energy, or it will lose both. So, in the early 1900s, a group of scientists, you can read more about this online, a group of scientists carried out an experiment where they put a radioactive isotope in a box that had a small exit hole in it, and this radioactive isotope contained unstable atoms with unstable nuclei, so they were emitting radiation, and that radiation would come out of the hole in the box in a certain direction, and outside this hole they had an electric field. Now it was a bit more complicated than just a single anode and a single cathode, but for demonstration purposes I'll just use a cathode and an anode. So you've got your positive end of your magnetic field and your negative end of your electromagnetic field. And what would happen is the radiation that was emitted from this isotope would come out of the hole, and they discovered that there was 3 paths it tended to follow. It would either go straight through the magnetic field without being affected, it would tend slightly towards the negative cathode, or it would bend very sharply round towards the positive anode, and it would end up actually spiraling round. This little picture that I've made, it doesn't show it, but it would spiral round. And now we're going to look at each of these 3 trends and what type of radiation they actually are relevant to and they compare with. So now we're going to look at the first type, which is alpha decay. The symbol for alpha decay is the Greek alpha symbol, and that's just because when it was discovered this is the symbol they used for it, and it just hasn't really changed since then. So it only occurs in large nuclei with more than 82 protons and a much higher number of neutrons. And what actually happens is, this is our nucleus here. Now this is not an accurate image of a nucleus, obviously. It will have a lot more subatomic particles in this and it won't look like this, but for demonstration purposes this is our nucleus. The red particles are protons and the grey ones are neutrons. And what will happen in alpha decay is this nucleus will eject an alpha particle. Now an alpha particle consists of 2 protons and 2 neutrons, So it has a nucleon number of 4 and a proton number of 2. You might also notice that this alpha particle is actually just a helium nuclei, so that's just something to note. So what happens is it will eject this, losing mass and a little bit of energy, and it will become more stable because it will become lighter and it will be a smaller atom, so the strong nuclear force will have more of an effect on it. So if we just look here, when an alpha particle is emitted, now we're talking about the nucleus here. If we go back to this nucleus, when this is emitted, what will happen is the nucleon number of the atom that the alpha particle was emitted from will drop by 4 because you've just lost 4 nucleons, and the proton number will drop by 2 because you've just lost 2 protons. And what this means is the actual element that did the ejecting of the alpha particle will change because it's lost some protons, so it will have a different proton number and therefore be a different element entirely. So if we look here, we've actually got sort of a general formula for this. X, which is the radioactive element, decays to form Y, which is the more stable element, plus an alpha particle. So if we say that A is the nucleon number for this radioactive isotope, Y will have A's nucleon number minus the 4 that it lost. This is the proton number for the radioactive isotope. And then Y is this new element, which will have the proton number minus 2 because it's lost 2 protons. And then of course this alpha particle here actually just matches up with that. So what we'll do is we'll have a look at an example now. I can't remember the numbers off the top of my head, but I'm pretty sure uranium is about, let me just change the colour. I'm pretty sure the uranium is about 238. I'm pretty sure it has a nuclear number of about 238. And this is obviously radioactive because it's going to decay. And it has about 96 protons, I think. This could be wrong, we'll find out in a minute. And what happens is it decays into thorium, and that has 238 minus 4 for its nucleon number, and 96 minus 2. So that ends up with a nucleon number of 234 and 92 for its proton number. And then of course here we've got the alpha particle, which is 4 and 2. So that's just an example. I'm going to just double check that that was right. Here, that's where I went wrong. This does actually have 92 and 90 instead of 96 and 94. So don't use the previous example I showed you, actually use this one here. So as you can see, it matches up with this up here, and they could give you a question like this in the exam. You just have to answer it as I've showed you, but obviously don't make the mistake that I did. So now, this is the experiment I showed you at the beginning. I'm going to show you the path that the alpha particle takes and explain why it takes that path. The alpha particle was actually the type of radiation that tended slightly towards the negative cathode. So you can imagine why this is. This particle here has 2 protons and 2 neutrons, so it actually has a charge of +2, which means it's going to be attracted towards the negative cathode. However, it only tends slightly towards the cathode because it has quite high mass for a type of radiation. It's got an atomic mass of 4, meaning that its specific charge is relatively moderate. If you want to know more about specific charge, that is also in another one of my videos. So it has a relatively moderate specific charge, so it will bend towards the cathode, but it won't bend straight towards the cathode. It will only tend slightly towards it. So now we're going to look at the next type of radiation. Beta decay is the second type of radioactive decay that was discovered, and it was given the Greek symbol beta just because it was the second type that was discovered. And it's actually known as beta minus decay because it was later discovered that there is something called beta plus decay. So what happens in beta decay is our nucleus here. What happens is one of the neutrons inside of this nucleus. So imagine this neutron is inside the nucleus. What will happen is it will actually decay itself into 3 different products. It will decay into a proton, which stays inside the nucleus. So this all happens inside the nucleus. It will decay also into a beta particle, which does not stay inside the nucleus. This is ejected out of the nucleus. And an antineutrino, which will also be ejected from the nucleus. So this is a bit more difficult to get your head around. So this neutron inside the nucleus decays into three separate things. The proton stays in the nucleus, but these two are ejected out of the nucleus. So you can imagine it's losing some mass and some energy when these two are ejected out. You may have already noticed, but a beta particle is effectively just an electron, given a funny name. So it decays into an electron, a proton, and an antineutrino. Let's look at this over here. When a beta particle is emitted, the nucleon number remains the same, because if you think about it, you've got a neutron turning into a proton all inside the nucleus, so you're swapping out one nucleon for one nucleon. So the nucleon number will remain the same, but the proton number will increase by 1 because you're getting a new proton, meaning that the element will change, but the mass stays the same. An electron antineutrino, which is this one here, is released, and you don't need to know about this too much yet because that is for a different video, but this is basically a small particle that is ejected that helps conserve the momentum, the mass, and the energy of this interaction. And when beta decay was first discovered, they couldn't prove it they couldn't definitively prove that this is what happened, because the momentum and the energy and the mass weren't conserved when this happened. But then the antineutrino was discovered by Pauli, and it managed to make everything in this interaction actually work. And all you need to know about this antineutrino is that it is very, very tiny, and it has no charge. It just helps everything sort of balance out in the interaction. So as I said before, as for the previous form of decay, we had a small little equation. So we have another one, slightly more complex here. Your radioactive isotope here will decay into a new element, a beta particle, electron, and an antineutrino, which is drawn using this symbol here, just a VE with a line over it. So the nucleon number of your isotopic, or your radioactive isotope, will not change when it turns to this more stable element. However, the proton number will increase by 1, and for the beta particle, it's got no nucleons and it has the opposite charge of a proton, so we say it's got -1 proton number. And then we've got the electron antineutrino here. Another thing just to quickly discuss is that you can probably imagine if this isotope, or this radioactive isotope, gains an extra proton but it doesn't gain another electron, it will actually have a +1 charge. And what this actually means is that for a split second it will actually be an ion, or will have a +1 charge. It will have more protons than it does electrons. And it's important to know that this electron that's been emitted is moving way too fast to be recaptured by this atom. So what happens is this will be emitted really quickly, but there will be a lot of other electrons around, and it will recapture a different electron. So for a split second it can technically be said to be an ion, but it will so quickly recapture an electron that it will neutralize itself. So in beta decay, this nucleus will be an ion for a very short amount of time, but it will neutralize itself very quickly with a surrounding electron, but not the one that it emitted. So we'll look at an example here. I don't remember the numbers for this one either, but I will just put those straight in. So as you can imagine, we're going to have two numbers here. This one's going to be the same. This one's going to be the same as that, +1. This is going to be 0, and this is going to be -1. And as you can see, that works just fine. So it's changed the element, hasn't changed the mass, and we've got our products here. Just the same as I did with alpha decay, I'm just going to show you the path that this type of radiation took when it was emitted into a electric field or a magnetic field. So we talked about specific charge a minute ago. If you look at the beta particle, it has half the charge of the alpha particle in the opposite, in the negative direction, but it has a very tiny mass, and this means that it actually has an extremely high specific charge, because an electron does actually have the highest specific charge of any particle, which means it won't just tend towards the anode, it will actually sharply bend towards this positive anode, and it will end up just spiraling around there. So that's the path that the beta decay, or the beta radiation, will take, and that is due to the fact that it has such a high specific charge. Moving on. The third and final type of radiation I'm going to be talking about in this video is gamma radiation, or gamma decay. And in gamma decay, there's actually no mass lost from the unstable nucleus. It's actually just energy that's given off. So if we've got our nucleus here, what happens is energy is given off in the form of an electromagnetic wave, or a gamma ray. So if we look at that here, an unstable nuclei either has too much mass or too much energy, and the way it can become more stable is to emit a gamma ray. This high energy gamma ray carries away some of the energy from the nucleus, making it more stable. So we're going to look at an example of that. In a previous video I talked about carbon-14 dating, and about how carbon-14 was a very unstable isotope of carbon, and that it decayed into more stable elements such as nitrogen. And you might be thinking this is beta decay, and that's because it is. This isn't gamma decay, this is just setting up the example. So we have carbon-14, which will decay into nitrogen, a beta particle, and an antineutrino. Now this little asterisk here actually just shows that this nitrogen is very high energy, it's very excited, which means it is actually slightly unstable. So what will then happen is this excited nitrogen will decay into more stable nitrogen. Nothing changes, the proton number and the nucleon number stay exactly the same, and the way you know it's decayed is because it's lost this asterisk and a gamma ray has been given off. So gamma rays don't change the mass, so these stay unaffected, but they do release, or they carry away some energy with them. Very high energy. So you probably guessed it, but we're going to look at the path that the gamma ray takes through a magnetic field. And you probably already know this, but you cannot deflect light or electromagnetic waves in a magnetic field. So it will just pass straight through. I know that's not a straight line, but just use your imagination. Imagine that passes straight through. So that's gamma decay. We're now going to recap the decays in this slide here. Here is the three types of radiation that we've looked at: alpha, beta, and gamma. So this alpha particle has a moderate specific charge. The beta particle has a high specific charge. The gamma ray has no specific charge. Hence this here. So if we just grab a pen, this one here will be the beta, this one here will be the gamma, and this one here will be the alpha. And we've already explained why this happens, so I won't go into detail on that again. One last thing I'm going to talk about is the sort of properties of these type of radiation. An alpha particle has a very large mass, so it won't actually be able to travel very far. It will travel maybe a meter or so in air, but you could stop it with a piece of A4 printer paper, and that would be enough just to stop this alpha particle in its tracks when it had been emitted. This beta particle is much lighter, so it will be emitted with a higher velocity. It's much smaller, so it will be able to travel further, and you'd actually need a sheet of aluminium foil to stop it. And finally, this gamma ray actually will not be stopped by much. It can travel miles in air, and you'll actually need a couple of meters or a couple of feet of lead to stop this. So that's quite interesting about those. They each have their own useful uses in everyday life, but that's more of a GCSE topic, and I probably will make a video covering the uses of these radiations just because it's interesting, but that is for another video. So that concludes nuclear decay. Thanks for watching.